Okay, so welcome. I'll try to keep this to about 35 minutes. It's a little bit more than I usually do, but we'll see how it goes. So I am a cognitive scientist, and I did my PhD like 25 years ago on modeling car drivers, and I was using semantic networks and lots of AI techniques. So it was all full-bloom AI 25 years ago. And then, of course, as you guys probably remember, we got into the AI winter when no one could talk about artificial intelligence. But it seems that it's completely back now, and I'm really happy to be here at Franz when AI is coming back again. And I'm going to talk about how we do cognitive modeling at Franz. So let me give you a little bit of a history of what actually happened in our field for the last several years. So, okay, so up till 10 years ago, I would say that most companies only had structured data in their databases, and there were already people doing interesting statistics and data science on top of the structured data. Of course, I don't even think that the word data science already existed. It might have. Spark was definitely not there. Machine learning was already there in AI, but don't look too much at this middle box for now. Yeah, and then what happens is you have your structured data, you do your statistics, and then the output of your statistics goes into reports, or people build applications on top that use probabilistic data, or things go into scientific publications. Yeah, so this was kind of the state. And don't pin me down on the years. Yeah, it might be a little bit off here and there. So then about 7 years ago, I saw that in our database world, unstructured data came up. So already in the 90s, someone had estimated that about 80 to 90% of all relevant data in the enterprise are actually not in your structured databases, but are in the unstructured data, like in your emails and Excel spreadsheets. And what do you have? Yeah. So it's also the time when big data and Hadoop and all of that came up, and people started to do analytics and data science and machine learning and what have you on top of the combination of structured data and unstructured data. Yeah. The results would still fly out to, well, go out in publications and reports and whatever and whatever. Then, about 4 to 5 years ago, we suddenly saw that there was a really big push to start adding knowledge to your data infrastructure. Yeah, of course, we in the semantic community, and I guess most of the people in the audience are from the semantic community. Of course, we're already using knowledge for a long time. Most of you probably were using already semantic graph databases. You were working with linked open data, vocabularies, taxonomies, ontologies. But then about 4 or 5 years ago, we saw that that Google started the knowledge graph, and Watson came up and started to win with Jeopardy. And so now we have this picture where, for really interesting applications, you use structured data, you use unstructured data, but you use kind of knowledge to tie it all together. Yeah? And then what you see in the last 3 years, and some of the things that we've been very actively working on, and I've not seen many other people do that so far, is that we started to feed back the output from machine learning, yeah, and put it back into our data infrastructure, and suddenly we have a learning system. And I'll give you a whole bunch of examples later this talk about how we now have data infrastructures where you have structured data and knowledge and unstructured data, but also probabilistic inferences are added to your data and just become part of the entire query framework that you can do and use. Yeah? So that's the other thing. We took all this data, okay, here it is, and well, and of course this is something that you think is pretty obvious if you're a graph database company, but we put everything into one distributed semantic graph. Now it's very important to realize that it's a semantic graph because we use all those vocabularies that are available and taxonomies and thesauri and ontologies, and we use linked open data, and we turn external public databases all into RDF and semantic graphs. Yeah. So, and we link that with our structured data and unstructured data, and I don't think there's any other technology that was really built to share, to integrate data. So, and then of course, our probabilistic inferences are just also part of the graph. And the other part here is that I want to stress it's distributed. So my first example that I'm going to give is about our semantic data lake, where actually we run on a huge cluster of machines where we distribute this whole mix of structured data, unstructured data, knowledge, and probabilistic inferences on a distributed AllegroGraph. Okay, and then all of this, I would say we can call cognitive computing. There might be other definitions of cognitive computing, and people try to describe it in a slightly different way, but this is definitely one embodiment of cognitive computing. All right, so this is a little bit of a history, and it kind of also makes clear how we mix all these types of data with data science and how we added learning to the whole mix. Yeah? So then what are the examples that I'm going to talk about? Well, the first one is in healthcare. We are working with a hospital chain in the Bronx called Montefiore. We have about 2.7 million patients in the database, 10 years of data. We use extensive, there's an extensive use of knowledge bases, both taxonomies and public linked open data and medical databases turned into triples. And then we can do new types of queries, and I'll show you a number of those. One of them could be, well, if I have this class of diagnostics, can I get this procedure? What are some of the new symptoms I might get in the next 2 years? Yeah, this is the kind of example I'm going to give you. We do some work in e-commerce and brand protection. So what we can do is, actually, I'll just leave it up to when I get to the example. But I can apply the same cognitive computing paradigm to logistics, to where we look at, okay, well, if a particular part breaks down, what are all the other parts that I really usually have to buy after that part breaks down? Then we do police intelligence. So this is kind of a really interesting area, but I can't say too much about it. But what we can do now is we have observations, telephone calls, location records, and all of that. We can use that to infer a lot of soft facts, like, okay, is this person maybe a member of this organization? This person maybe meet that person. What is the chance that this person actually knows this person? It's all put together, and now you can take any two persons and find, for example, if you want to know if there was a communication between criminal 1 and criminal 2, we can find a temporally ordered shortest path between two criminals, not only by looking at the hard facts, but also looking at inferred soft facts. And finally, I could talk about fraud detection, where we have a complete chamber of commerce from a country in Europe, but we also have the Panama Papers, and we link these two together through probabilistic relationships. So these are the examples that I'm going to talk about, but my emphasis will be on healthcare. So let me go there. So as I said, we're working with Montefiore and Einstein Medical College in the Bronx. And it's probably the 8th largest hospital in the United States. And what we're building there is a cognitive computing platform for every type of healthcare analytics. Yeah. So normally when you're a hospital and you want to do personalized medicine, you can go to at least 10 different companies, yeah, that want to sell you personalized medicine. And your biggest problem that you're going to get is that the company that you go with then needs to take all the data in your hospital and massage it and put it in the right shape, and then they can do personalized medicine. Yeah. But say you also want to do predictive modeling, so then you have to build an entire new data model and a new data system just to be able to do predictive modeling. And so, yes, you can find a vendor for each of those, but you would wind up in a chaos of data models. So what we're doing is we're building a platform that makes it very easy for other vendors and for ourselves to do any of the techniques that you see here and do it on what we call the semantic data lake, or our cognitive computing platform. I already told you, so we really believe in the data-centric approach. We have 2.7 million patients with 10 years of data in the database, and all the data is captured in what we call a unified clinical event model. So there's many different ontologies around where people try to capture everything that happens in a hospital, and they look like big master data management schemas and where you try to reflect what happens in the hospital, but we've tried to come up with a very simple model where we turn everything into an event. And so we have 350 types of these events. One type of event might be a diagnostic. Now, of course, the diagnostic itself then might have 20,000 values, you know, for all the ICD-9 or ICD-10 codes. So each class can have a lot of, well, types or subclasses. But anyway, the basic model is simple. And so what kind of data do we put in the semantic data lake? Well, there's a lot of data that's both structured and unstructured. Here's a picture from my partner at Montefiore that he always likes to show. Yeah, so we have our patient here. Yeah, and nowadays when the patient goes back from the hospital, they sometimes even give them an iPad or a machine so they can communicate better. People might have the Fitbit or Apple Watch. We now know a lot about your genetic makeup. We know your family history and your family tree. There's been devices implanted in you, so we get the Internet of Things. Yeah, things that all the time generate data. Montefiore just started using Epic, which is the kind of the elephant in the world of ERP systems and electronic medical record system in the hospital world. We have ICU, where all these devices generate continuously data. We have test results. We have analog data. We have imagery that we put into the semantic data lake. If we do a post-mortem analysis, it goes in the database. It's the pharmaceutical data. And there's a call center, so actually that's very important. Once you get out of the hospital, especially if you want to avoid readmission, it's very important that the hospital checks in with the patient every day after a procedure to make sure that they don't get back within 30 days. So you want to ask if they took the pills, how they're feeling, if we need to send you a nurse, etc., etc. All that data, outcome data, also goes into the semantic data lake. The insurance forms, and I could go on and on. I don't want to go too deep here, but it's really humongous data, and it all goes into a graph. Now, looking at the list of people that are in the audience, I think many of you have already seen our tool Graph, yeah, our visualization tool on top of our semantic graph database. Let me just show you the simplicity of the data of how we put our data in the distributed AllegroGraph. Yeah, so we have a patient, and of course everything is hashed because of HIPAA rules. This person is of type, well, this thing is of type person, and then there is a, this person had an outpatient encounter. So on the left hand, by the hand side, you see the colors of the classes, and here you see the names of the predicates. And this outpatient encounter was at this particular time, and then this patient had a diagnosis, and the diagnosis was allergy to peanuts. Yeah. Everything, all the structured data is basically structured that way, that patients have encounters, whether it's an inpatient, outpatient encounter, ambulatory, and then you have a diagnosis or a procedure or a test or a measurement or whatever you can think of, but it's always this kind of measure, always this kind of event, and then ultimately you get grounded into, well, for diagnosis, into ICD-9 or ICD-10, and then for people that are familiar with thesaurus systems, then the allergy to peanuts is linked to a mapping object that then links to SNOMED, MMesh, and UMLS, and all the other systems. We have more than 180 of these systems. And so every ICD-9 or billing code, sorry, I went a little bit fast. ICD-9 codes are, or ICD-10 codes are the billing codes that the hospital sends to the insurance company. And we link them to medical terminology, so we have more than 180 terminologies, all combined in a huge graph. And so this allergy to peanuts is in its cost hierarchy of allergy to legumes, to food allergy to substance, to allergic disposition, to all the way here. Yeah? So structured data, and then here the knowledge base. But I'll talk more about the knowledge base. And then our data is another thing that we do in our entire database, is to make sure that we can also always trace back where data came from. So if we have a person, there's an outpatient encounter, and there was a diagnosis for this encounter, then actually we also specify when we did the ETL procedure from what table and what column the data came, yeah? And then everything else that's relevant to that particular, just that particular field and this particular diagnosis. Yeah? So everything, provenance for every data element. So that means like almost 75% in our semantic data lake or distributed AllegroGraph is actually provenance data. Okay, so I talked about the structured data. Then there's the knowledge base. I said a little bit about it. It's a combination of more than 180 vocabularies and terminology systems. And they are ultimately all linked to the billing codes, ICD-9 and ICD-10. So that is the link between the structured data part and the knowledge base part. Then we have external databases like PubMed turned into triples. And we have linked open data that you can download for the web. So we have many types of data that we can link with the structured data. And everything is linked through SCOS. This is for the few people here in the audience that actually probably know what SCOS is. Here's a picture, and I'll leave it into our presentation. This is public material where how we link the URML list to the SNOMED and to OMOP and to LOIC, etc. Yeah. So this has been a huge effort to make sure that ultimately everything is kind of interlinked in our knowledge base. And here's another picture to show. So if you think of this cloud here as the structured data, yeah, like a patient has an inpatient encounter, there's a diagnosis that had the diagnosis, then and he got a particular drug. Then here you see that ultimately we have the drug codes and drug classifications. We have the diagnosis codes and the diagnosis classifications. We have genetic profile, the procedure codes, and that is then all linked to external, well, not external, but it's still in our semantic data lake, but publicly available data and some not so publicly available. Yeah. So we call this whole thing the knowledge base. You had a combination of taxonomies and external available databases. Then of course we have all the data over time, and because it's so important, we also link the census data and other socioeconomic data. And then we have this whole feedback loop that I'm going to talk about later. Okay, so why is it important, yeah, to link these the structured data about patients with the knowledge? Well, just think of this query. Yeah? By the way, what you're seeing here on the screen is what we call our visual sparkle. Yeah? We can create queries just by drawing these pictures on the screen, and it will automatically turn into sparkles. So here we say, well, there's a person that had an encounter, that had a diagnosis, which corresponds to a diagnosis value. This is the billing code, which maps to an object that maps to a concept, yeah, which ultimately is the child of a concept called aphonia, the inability to speak. Yeah? And if I do this query and I just do one step up in the database, if I just literally do this query, then I get a few patients. I find that for the SNOMED codes for particular types of aphonics, I get 193 and 32. But if I use this here, the little plus sign, so I really use the power of the knowledge base, and I say, okay, I want to link all the concepts ultimately related in my knowledge base to this particular concept of aphonics. Yeah, so I use path expressions in Sparkle, or so like a little bit of reasoning here. Suddenly I get far more results. Yeah, because I'm using the power of the knowledge base to find these results. Yeah. Okay, but the core of my talk was about probability, so let me get there now. So why is it so important to add probabilistic inferences? I guess most of you guys already understand why it is important, but just for completeness, yeah, usually the output of data science goes into reports and publications. But there's actually not a formal trace where the data came from. By formal I mean a computerized version, or a version that is on the computer that you can share with other people, and they can actually use your data again to redo it or extend on it. There's also no formal link to the actual methods you used, whether it was Spark ML or an R script or whatever, or who did it or when you did it, and not even why you did it. Yeah, and you can't compare it to an earlier result. So you do the same method again a year later. It's very hard to compare it with the computer. I mean, you could look at the publications and try to visually look at the differences, but you can't use your computer to define the difference in the results. And also important is you might do, and I'm going to show you this in the examples, but if you do some, say, a cluster analytics, yeah, then if you don't put it back in your database, then you can't use that as the next step for a follow-up analytics. Yeah, so basically what you want to do, you want to use the output of data science as building blocks so you can do more data science on top. Yeah. And then another point is, and this is just a general point, is that the output of your data science is just not queryable. That is a correct English word. Yeah, and this has all kinds of disadvantages. Yeah, you can't reproduce your research findings. There's problems with security and compliance, and most importantly, there's a lot of duplication of efforts. So anyway, that's the importance of putting the inferences back in your database. So let me give you the first demo. And so I have on my laptop a VM here with part of my healthcare data running. Let me start Graph. Clean the screen. So this is Graph, our tool on top of AllegroGraph. And what I'm going to show you, well, first I want to do a little explanation. So a friend of mine has a 4-year-old, and about, I would say, 3/4 of a year ago now, he gave his kid a spoonful of peanut butter, and the kid instantly went into an anaphylactic shock, had to go to the hospital 30 minutes later, and they barely saved his life. And then the doctor looked at his medical charts and said, you know, I could have predicted this because peanut allergy goes always together with, well, this kid has dermatitis and it has asthma, and that always goes together with peanut allergy. Yeah. So my friend came to me and said, Jans, you got all this data. Can you actually see if this is really true? So what I did, he said, okay, let me try. And I took all the data from that we have about diagnostics, and I computed the co-occurrence between each diagnostic. So how many times in my database does someone have a broken leg with a blind left eye, yeah? And how many times do you have dermatitis and asthma? Yeah, so you get a number for each. And then you look at the distribution of each of the diagnostics, and you look at the co-occurrence, and you say, so how strong is this co-occurrence? Is this something that is just that I could expect by chance, or is this a really strong? And the name of this measure is the odds ratio. You see here, yeah. And for those that are familiar with data science, this is the Wikipedia description. You can look that up yourself. Yeah, and here is the basic table where you compute. You might have the peanut allergy, the number where you both have peanut allergy and ingestion to dermatitis, or where you do have peanut allergy but not dermatitis, or you don't have peanut allergy but you do. Anyway, you get my point, and then you compute this thing called the odds ratio. So once you have these odds ratios, I turn those back into triples and back into distributed AllegroGraph. Yeah, and here is when I did this for the first time. So basically I created this query, odds ratio for peanut allergy. Yeah. So this is a visual query. It says, if given that I have allergy to peanuts, yeah, give me all the odds ratio objects that point to another ICD-9 code. Yeah, and when I run the query, I mean, I was blown away when I did the query for the first time, because this was exactly what the doctor said. Yeah, If you have peanut allergy, then the odds ratio for dermatitis is 2 to 10. Yeah, that means the co-occurrence is incredibly large. And then asthma was high. Another type of asthma was high. Then we have another type of dermatitis, and finally acute upper respiratory infections. Yeah? So this was just exactly what the doctor said. I can turn this into a visual graph. Yeah. Yeah, so you probably realize that this is the same picture that you just saw. I like to show it this way. And then the next thing I wanted to do, or what my friend wanted, is he wanted to know if these symptoms related to allergy to peanuts are related themselves through odds ratios. So, well, I said I can easily do that. I can highlight these new symptoms. I choose the predicates from 2 and from 5 and to 5, yeah, and I hit the button Shift F here, and I basically compute the shortest path through odds ratios between all of them. And what we saw, yeah, is we get new symptoms, only 5, yeah, and they're still related. It's allergy again, it's viral pneumonia, close to asthma, allergy to milk products, eczema, which is another type of dermatitis, and then the common cold. And if I would do it one more time, and I will do this, oh, 1 second, then I could get only 2 more factors. I will get wheezing and asthma. Wheezing is obviously related to asthma, and asthma is related to asthma. Yeah. So now I have like a perfect cluster around the concept of allergy to peanuts. Yeah, and I can do this for anything. So one thing I like to do for audiences is when I do this, I take, say, lack of housing. So this is a visual query that says, okay, oh, so by the way, this is something we run in the Bronx, and there's quite some people without housing, yeah, and so lack of housing is an ICD-9 term. It's a context term that specifies that, for example, you're homeless and you need antibiotics, then instead of pills you get a shot, yeah, and so for the billing you have to use this code. Anyway, the thing is now, lack of housing, yeah, given that I have lack of housing, what is the most related thing to lack of housing? Yeah, and then how are this concept, can I find a link to itself again? Yeah, so is it related to other concepts that all are related to the concept related to lack of housing? So I can run this query, and I get a graph that I see here, and so you probably are still guessing what is the most common thing. Then what you find that it's actually all related to cocaine abuse, cocaine dependence continuous, and alcohol. Yeah. So I can take any concept, any disease that happens in my 2.7 million patients, link it, and then say, so how is it related to every other disease that I see in my patient data? So let me go back, yeah, because another thing I wanted to show you is that, so this was the allergy to peanuts and how it related to all these diseases. But each of these terms is, so these blue things are ICD-9 terms, but they're related to the knowledge base. So how are they related to the knowledge base? Let me show you. So each of these terms has a exact match. And let me take this one. And this thing, so this is the exact match. That is the mapping object between billing codes in the knowledge base. And then I can look at the child. That this concept is a child of some other concept. So now we're going into a SCOS hierarchy. This thing is then again a child of something else, dermatitis and eczema. And I could go all the way up, yeah, to whatever I'm interested in. I can do this also. I could also do this a little bit more automatic. I could say, well, let me find the links in the knowledge base between, say, eczema and this particular dermatitis here. Yeah, and it finds automatically a link. Or I could say, how is this asthma related to this eczema? And this one has to search then, because this is a much longer search, because it goes through, in this case, about 350 million triples. and it finds that it ultimately all linked to hypersensitivity. Let me show you a little bit better here. Yeah, so we have here the astringent asthma, we have here dermatitis, and it ultimately all links together through this concept of hypersensitivity. Anyway, so this is a basic demonstration of how you add probabilistic inferences back into the database, and now you can link it with whatever you want. Yeah, so let me go back to the presentation. Actually, now let me give you another example. Say, another example of how you actually can do queries, because what I showed you so far was discovery and graph. But how can you do a query where you mix the knowledge base and the probabilistic data? So I could do this, yeah, and this is a query, and let me just do this in English. Yeah, you say, find in the knowledge base everything related to diabetes. Just find all the ICD-9 terms that are related to diabetes. Then also find all the ICD-9 terms that are ultimately related to something with vision, eye, or retina. Yeah, and then between these two sets, find the odds ratios between things related to diabetes and things related to vision. Yeah, and so I do this query, and this is a huge search. Normally, but not in the demo, I actually use the child relationships here, and I use the path expressions, so you get even more results. Anyway, it doesn't matter in this case. And then I get a visual graph of, and this is for researchers that kind of want to explore how do these two domains actually link in my patient set. Yeah, and now you can see that this diabetes, this type of diabetes, it's called, anyway, you can read it on the screen. Yeah, it's related to unqualified visual loss of an eye and unspecified retinal detachment, retinal hemorrhage, and some other thing here. Then you go through a lot of terms in the knowledge base in the taxonomy system, and ultimately you get back to other probabilistic relationships with polyneuropathy, diabetes, another type of diabetes, etc. Yeah. Now, there's no way we can talk about what this actually means today, but you get my point where we do a query you could never do before, and that is link a knowledge base through actually empirical data. All right. So we've done this. I showed you an odds ratio, and I'll keep this in the presentation so you can look at this later yourself. We also did, and we've done many, many different techniques. I'll show you two more. One is the association rule. So people in the audience familiar with data science know this technique. So if I buy onions and potato, it's also very likely that I'm going to buy burgers. Well, in healthcare, yeah, you have, well, by the way, we did an analytics here where, so here and this is important to see, we actually store the metadata about a particular analytics. So we have an analytics that was done at a particular time, done on a selection of 1/32 of the data by a particular person, the technique used in this far more, I'm just showing you a little bit, yeah. And then here we have lift is like odds ratio, but then for association rules. So this one says if you have acute kidney failure and severe sepsis, then very likely you get unspecified septicemia. And then another rule might say, well, if I have unspecified septicemia and septic shock, then I might get an acute respiratory failure. Yeah? So now you get almost like a Markov chain or a Bayesian network through your data. And then another point I'm not showing you here, but one thing we're really careful about is that when we put our analytics back in the database, we make sure that we use the quad of the triples to specify the name, well, the ID of the session that we did. So we make sure we take all the metadata about analytics, put it in the database, including the scripts we use, when we did it, etc. We make the fourth element the name of that particular session. So now if we want to delete all of it, we just can delete them, or if we want to compare with another one, we can actually use that session ID to now start comparing analytics. I hope that makes sense to some of the audience. Then another technique is we did k-means clustering, and again, you can look up on Wikipedia what it actually means, but you want to find clusters in your data. And the wiki has great examples of what you can do there. And so for this for us it means, again, we have an analytics number 2 with some metadata, which is a k-means cluster, which is a cluster. Here are the main factors of the clusters. Yeah, so the biggest one is pure hypercholesterolemia. So this is for cluster 1. There's multiple clusters showing you only one. And here are the other factors in this cluster. And then these things, these colors, are people. So a cluster not only has factors, but also people that are part of that cluster. So we take, just for fun, one person in the cluster, and then we look at an encounter where the encounter has a particular billing code. And then what I can do is I can take this type of analytic and I can use the odds ratios that I used before. Yeah, so here one factor was diabetes with links to the billing code. Here we go to the billing code, and then I can actually use the odds ratio to say, okay, how is this thing here related to this thing here, just to odds ratios, yeah? And I find this result. So now you see an example of we combine multiple types of analytics. Again, not very meaningful in this context, but just to show off that it's possible. And then a query that I just showed you already on the screen, so I don't have to do it again, but this was the query where I showed you how you can find the statistical link between diabetes and vision problems in a semantic data lake by finding the set of ICD-10s that are related to diabetes and to vision problems, and then we show how we relate it in odds ratio space. And again, I leave these 2 slides in my in my presentation, so you can have a look at it later. Yeah, and here's then a picture of the result. And then some other examples, and I'm going to keep it very short. I don't want to go too deep. One is in e-commerce. Yeah, so you might have a manufacturer, yeah, that produces, say, something like Pose anti-aging cream, yeah, and the original manufacturer has an extensive description of the product, but then there's multiple small companies that try to sell that on eBay, on Google, on Amazon, and for some reason they all use a slightly different natural language description. Sometimes they use a different picture. The big marketplaces like eBay, Amazon, and Google force you to use unique product codes like ASINs and GTINs and all of those UPCs. But the issue is it's hard to do that, and people do fraud. Yeah, so basically you claim to be a more expensive product by claiming or stealing a product code from a much more expensive product. So we were asked is how can you visualize, yeah, from a brand protection point of view, how visualize what's actually happening with our product. So one thing we did is we computed, first we searched with a very coarse way for everything that has, say, a La Roche-Posay Redermic cream. We find it on all these marketplaces. We compute the similarity between all of them, and then we can actually do queries on top where we say, okay, find products that are highly similar but use different product codes. Yeah, that's one way to just find if people were being fraudulent or just didn't know how to do the right product codes. Or you can look at your pricing. Yeah, so there's many ways, but because everything is uncertain with the listings on the pages on eBay, Amazon, and Google, you can't just do a compare. You really have to use similarity measures to link it all together. So that is a project we did using this. We did a logistic project, yeah, for huge trucks in the army, and what the customer is really interested in that, okay, I have a lot of repairs. To begin with, just first make a kind of a distribution of when a certain part gets breaks, yeah, and then if it breaks, what are the most likely things that I have to buy, yeah, that also will fail or that I have to buy in the near future, say in the next 2 months. So the same approach that we use for diseases we can also use in logistics. Yeah, what is the likelihood that this thing breaks? I have to buy these things in the very near future. So this is a logistic one. And then finally, my final example, then I stop, We also have a large database with the complete chamber of commerce. Yeah? You can get it online mostly through an open API, and say we want to do the query, yeah, and we want to do fraud detection and find if people are engaging in shell games. I'm assuming that you know what it is, where a person is controlling a company that starts another company that is a stock owner in another company, yeah, that then finally, where the lowest level company does something really bad, quickly goes bankrupt, the two companies above also go bankrupt, and then the guy at the top claims all, but has complete deniability. Say, well, I was just investing in this company, I had no clue what was happening 3 levels down. Yeah, so here's a visual query. We say there's a guy, yeah, that performed a role, and we don't care what kind of role it was, for company 1, where company 1 performed the role of full stock owner for company 2, and company 2 performed the role of full stock owner for company 3. Yeah, just a query just to find that. And if I do this, I get a result in my table. Again, it's a graph. I know it's a graph, but you can't look at a graph in a table. So if I click on visual graph, I get the same picture again, and I find that this particular guy, which is a frontman, is an executive in a company that is a full stock owner in this company, which is a full stock owner in this company. Yeah, and then for multiple directions, and this is the graph view. I can also do it as a tree view, and you see how this guy controls a lot of companies that own other companies. Now, how does it relate to the Panama Papers? So we have the full Panama Papers. We turned it into triples, and the issue was that in the Panama Papers, people use different names. Well, names for addresses for the names themselves, names of companies, but they're always completely misspelled. Yeah. So again, we had to do some disambiguation to find out whether one person is the same as the other person, and then you still don't know. But at least the investigators really wanted to know, help me to at least find the candidates that I might want to look at. Yeah. So here is a query that we do on a combination of a federation of the Panama Papers and the Chamber of Commerce, where we say, well, there is a Dutch entity that has a name, yeah, which is similar to a name in the Panama Papers, yeah, where there's an entity that has an address, where it has an address which has a similarity. It's the same thing as the odds ratio here. It's the same as this particular Dutch address, and then we have a temporal extension for addresses. Anyway, I know no one in the audience will be able to follow this, but it's such a beautiful query as a circle. So basically this query is saying, find people in the Panama Papers and the Chamber of Commerce that probably are the same, and then I can do the query and I can start looking, and other researchers can start investigating by looking at how people in both databases might be the same. Yeah. Then we'll run completely out of time, so I will skip the police example. And then I just want to summarize. This is the new paradigm of computing. I think that most of you guys will do this in the near future, and we're here to help. So Craig, any questions?
Yeah, let's start off with this one. Make it bigger.
Are these probabilities and provenance on the linked products are only on the instances? Well, every probability in the database is linked to a data science session. Yes, so we have, and then for every or most of these sessions, we also have link backs to the patient. Yeah, so if we do an odds ratio, or say a cluster, then we have a session for that, for the cluster and analytics, and we have a link back to every patient that was part in that analysis. So we have the provenance for that, or we just use a date. So that at this particular, we use all the patients that were in the database at this particular date, or we have the Sparkle query that said, okay, this is the way we selected the set of patients. And so we always have full provenance from a probabilistic inference to where it actually came from. Very important. Another question is, and I have to interpret it on the fly, you said the graph element is used for analytics provenance. I'm using the graph already. Alternatives. That is a tough one. So, well, I promised Craig not to talk about it, but then I will have to talk about it anyway. So Franz is working on a new technology that will come out in probably August or September, and it's called triple attributes. And what it is that for each triple, we can add a number of attribute values. Yeah, it's like a property graph database. So you have a triple, and for each triple can have a set of. So you could have add a date to every triple, or you could have the security clearance level to a triple, or you could have the session ID as a property. Yeah, and we also had to create our own syntax for this. So now we have n triple files. Where at the end of the n triple, we have a JSON object that specifies the key values, and you can both read it in and you can read it out. So this is one way to solve this problem, yeah, where you just specify the session ID as an invisible, well, as an element, and at some point if you want to delete it, then you just say delete all the triples with this particular triple attribute. Yeah. But there will be many talks about this in the near future. Can you explain your ontology use for the probabilities? Yes. In the semantic data lake right now we use an ontology that specifies all the metadata that you need to store for a session, like who's the author, what time, the why, a comment, the type of R script you use, the Sparkle query to select it, the backlinks to the patient. But there must be some data scientists in your audience, so we're also working on a RDF specification of data frames. Yeah. So you can kind of build RDF a mapping from triples to a data frame, and ultimately also a mapping from a data frame back into triples. It's a little bit like the other mapping schemes that people have to get triples out of relational databases. But this is actually the other way around to begin with, yeah, where you have a triple store with values, and now you want to turn that into a data frame that can be used by SparkML or R or whatever, or KNIME or whatever you have. Okay, and then can you say how the ratios are encoded in the triple store? It looks like R is a resource, the predicate is linking to the others. They're a resource for 230, 15, other for 70. Okay, so if I go back here, let's see if I have an odds ratio here. Yeah, here's an odds ratio. So this odds ratio, basically, if I double click on it, you see a from, and I actually created I took the top 5 for demo. It's better to look at the from 5, but the top 5. But usually in my analytics, I just use all the froms higher than 2. Yeah, and then we get the label, the actual odds ratio. I have other versions. This is an early version. I also have the frequency. I hope this answers the question. Yeah. Is provenance automated by data lake, or is it dependent entirely on the user system doing the inference? This is something that would be the topic of an entire other talk. But basically, we have a declarative mechanism. So we have this unified clinical event model of 350 types of clinical events, yeah, and they're specified right now in top-rate composer with a visual interface on top. And then we also have declarative mapping objects for each attributes of each event object that link to the right database, table, and column. And that particular ETL procedure could be generalized to any type of database, but right now we're only using it in healthcare. Automatically adds all the provenance statements. How are you better than Neo4j? That's a very leading question. I probably should not answer. Let me say in general about property graphs, and this is something that I specified in my presentation. Once you see the importance of using linked open data, the use of vocabularies, the use of terminologies, yeah, ontologies, of being able to take data sets from different places and automatically integrate them together, then yes, of course you could use Neo4j, but then Neo4j would have to reinvent the semantic web, yeah, reinvent ways to come up for naming schemes for nodes and naming schemes for the links between nodes. So, I mean, yeah, they could do that, but then they would reinvent the semantic web. And what would you then prefer, the semantic web from Neo4j or the W3C semantic web? Yeah, that's just yeah, that's a tough question. Easy question. What product, okay, the final question, what product creates the visual Sparkle query? Do I need a special plug-in? No. No, this is the tool Graph. Those are still on the line. This tool Graph is a thick client, yeah, that you can run on Windows and the Mac, Linux, and it has what we call the graph screen. Oh, actually, this is, you've probably never seen this, but I can actually take a billing code. I take an odds ratio. I take another billing code. When I do Control-I, oops, let me go back here. Control-Z. Let me go back to the graph. Yeah, I can take part of the graph and stick it into what we call the graphical query view, and then I can just take and turn some things in odds ratio 1 and say new node variable from 1, and then run a query, and I get my results here. Yeah, automatically a Sparkle query gets written, and then the results are here. Yeah. Okay, and one more. Is there an overlap between the concepts you presented and the reasoning power using methods such as description logic? Any particular interest in discovering missing data and incongruent data? Let me look at it. Okay. Yeah, we use, so in the knowledge base we use both SCOS and SCOS. Sorry, SCOS is probably how to pronounce it. SCOS and OWL. And we do sub-properties and we do subclass reasoning. However, we have materialized all that knowledge. Yeah, because if you have to do this on the fly and you want fast answers, that's just not going to happen for that large data. So we use materializers to materialize all that knowledge. And then the other question is, any particularly interested in discovering missing data, incongruent data? Of course, in data science, it's incredibly important that you deal with those things. So in the description language that we're going to have for the mapping between triples and a data frame, there is also something for what you do with missing data. Yeah, and then ultimately, at some point, we're going to implement the shapes, idea of shapes, but I guess that's the answer. Okay, hey, I answered a lot of questions. I think we should keep it to this. If you have any more questions, please send us email, and we'll make this talk available within 1 or 2 days. What is the usual? Yeah, okay. So within 1 or 2 days, this talk will be available, and the slides will be available. And thank you for listening.